Hi everyone, my name is Vicki and I'm a senior software engineer at Discord. Today, I'm really excited to chat with you all about how Discord indexes trillions of messages in search, and specifically to share some lessons learned from scaling our search infrastructure. So back in 2017, we first introduced messages search to Discord. It was a really often requested feature, and so our team took on the challenge of designing a system that could handle the then billions of messages and allow users to efficiently search messages in their servers and DMs. We chose initially to use Elasticsearch to run our search infrastructure. We evaluated some managed SaaS solutions, but they were generally a bit expensive, and we were also hesitant about having our user message data hosted with a third party. Of the open source solutions at the time, Elasticsearch seemed to be a good fit, and it was one that members of our team had experience with. One design decision that we made from the get-go was to lazily index the messages for our resources. So there may be, as you can imagine, many DMs and guilds that are just never searched, and we only want to index resources that are actually serving search requests. So we lazily index and add resources to our search system, doing a historical indexing on the first request, and then indexing in real time all subsequent messages. Additionally, we chose to build a messaging queue to handle real-time indexing. This allowed for indexing to happen asynchronously and also allows for workers to pull batches of messages for more efficient performance and indexing into Elasticsearch. And finally, we made a key design decision to shard our messages by guild or by DM. So from a product perspective, we outlined that messages would be searched only within a given resource. So you can only search for messages within a guild or within a DM. Given that constraint, to optimize performance, we want to store all of the messages for that research on the same Elasticsearch index, mainly to ensure that search requests don't have to fan out across the cluster when we serve search queries. So what does this mean? An Elasticsearch cluster is composed of nodes, or servers that run Elasticsearch. Logically, Elasticsearch organizes its data into indices. An index is sometimes compared to a table in a relational DB model, and can also, in that vein, be thought of as a kind of logical namespace. In our usage in Discord, we think of an index mostly as an abstraction that groups together a set of Elasticsearch shards. An Elasticsearch shard is an instance of a Lucene inverted index, which ultimately provides the underlying fast and efficient search service. Elasticsearch shards follow a primary replica model, where there's one primary shard that is then replicated to n number of replicas. So here you can see that we have a cluster with 3 nodes and 2 indices. Each of these indices has one primary and one replica shard. And it's important to note that while an index can live on many different nodes, a shard lives on just one node. So all of the data for a shard is always co-located and on a specific node. So a lot of usages of Elasticsearch that you might be familiar with use indices as logical groupings of data. So in an application where you have, for instance, users and orders, you might have one index for users and one index for orders, or something kind of following this model. In this model, you can horizontally scale as your data grows by adding more primary shards to your index. And you can also scale, of course, by adding more nodes to the cluster to host those shards. So here you can see our index A actually has 3 primary shards that live across these 3 nodes, and we could add more shards to this index as it grows. It's important to note that in this model, as we increase the number of shards, this means that each query has to fan out over more nodes. So every search query to index A here must talk to all 3 nodes in the cluster, since each node only contains one shard, which has an incomplete set of all of the data in the index. So for our search use case at Discord, we have a slightly different set of requirements than kind of the typical Elasticsearch data model that we described earlier. We only query within a given guild or DM, so there's a pretty constrained size to the data that we'll search for a given query. So while our total set of messages can grow very large, each guild or DM is small enough that we can expect it to be housed within a single shard, and because of that, a single node. So we choose instead to constrain all of our indices to contain just one primary shard. That way we can treat an index as really just an abstraction over the shard and its replica. So that way we can create a set of indices for our cluster and then map the guilds or DMs onto those indices as they're added to search. This means that a search query for a given resource, so for a given guild or DM, will only ever need to talk to one shard, and thus just to one node, which makes our performance for both indexing and querying a lot more efficient. So in our model, as we scale, we can add more indices to the cluster, which increases our capacity to store more data, and we can also accordingly add more nodes to house these indices and primary shards. So now that we kind of understand how the V1 of Discord search works, we can take a look at how we did. Overall, the system performed pretty well. We were able to handle indexing up to 50,000 messages per second with no problem under normal conditions. Unfortunately, our system proved to be pretty brittle to single node failures, so a single Elasticsearch node failing could cause indexing delays across the entire system. In terms of query performance, we also had pretty good, but not perfect, not super great query performance. Our medians were around 500 milliseconds, but P95 and P99 crept closer to 1 second. Really, the biggest sticking points were around reliability and operability. The large impact from single node failures also made it so that we had no good path for software upgrades or rolling restarts, since our system was really brittle to node unavailability. So first, let's talk about indexing performance. If you'll recall, we index our messages in batches that are pulled from a single queue for all Discord messages. This means that a given batch will have a mix of messages that belong to all the indices on our Elasticsearch cluster. So here we have our example cluster, which has 4 nodes, which hold our 4 different indices. And you can see that our message batch has some various messages from each of these indices. So now let's say that node 4, which has the primary shard for our index M4, goes down. We can expect the messages living on M4 to fail to index. But unfortunately, in our batch model, this means that all of the messages in this batch and any other batches with messages on M4 will fail. So if we have, let's say, a 100-node cluster and we index batches of 50 messages, a single node failure means that around 40% of all of our bulk index operations will fail. So this makes our system very brittle and has very little tolerance for node failure. So this was a key problem in Search V1 that we encountered. And so as we looked forward to a new system, we wondered if we could instead route messages so that we could bulk index in batches of messages that live on the same index. So to accomplish this, we built a new message router in Rust. This router would spawn destinations as it pulled messages from our PubSub queue and establish a send-receive channel per destination. So in our search use case, these destinations are the ultimate Elasticsearch index that a message belongs to, which we define by the message's guild or by its DM. Now that we have our destinations, a message receiver could then pull chunks of messages all belonging to the same destination and index those. So in this way, we can localize our indexing failures in the event of node unavailability and improve the robustness of the system overall. So in our previous 100-node cluster, if one node fails, now only 1% of our bulk index operations should fail, since it will only be the batches that are going specifically to that index. Another key problem that we ran into when operating our Search V1 system was the increasing cluster overhead as our amount of data and as our service scaled. So in our Elasticsearch cluster, we defined nodes with different roles. We have ingest nodes, which act like load balancers and coordinators for the cluster, which receive both indexing and search query requests and route them to the correct nodes. We also have master nodes, and the master node is responsible for all kinds of cluster coordination. And in Elasticsearch, a single master node is elected from a set of master eligible nodes. We ran our master eligible nodes also as data nodes, which perform the bread and butter operations. So these are the nodes that actually store the index data in shards and that ultimately serve our search requests. Because our clusters were running and electing a master node from the set of data nodes, the master node would be performing coordination in addition to serving indexing and querying requests. So as our cluster grows, as the number of indices and nodes increase, it has higher coordination costs. And we saw that this became a really common source of node overload. So our master node would commonly become unavailable and fail, causing the then larger cluster-wide and system-wide impact. Additionally, as our data grew, it also meant that we had larger indices. This means that for each query, we have to scan over more data, which ultimately increases query latency. So smaller clusters and indices seemed like the right solution to improve performance, but also to further improve our failure isolation. So in our new system, we chose to split out 3 separate pools of nodes: our ingest nodes, which I mentioned earlier, a set of dedicated master eligible nodes that had no other responsibilities, and data nodes. Then we defined a cell as a set of many smaller clusters. A cell would own a logical set of data, for Discord, something like guild messages or DM messages, but house that data over many smaller clusters. Of course, having many more clusters and different types of nodes means that we needed better tools to operate and orchestrate these clusters. We chose to run these new clusters and cells on Kubernetes using Elastic Cloud on Kubernetes. This has made operating our clusters far more ergonomic, has made it easier to define our cluster topology, and also to perform upgrades and other operations really easily. Also, with our many cluster cells, we could define separate cells to store different kinds of message data. We created a cell to store guild messages and a separate one for DM messages. This allowed us to shard DM messages by user. So the searchable resource now is not just a given direct message, but a set of all of a given user's direct messages. This is what powers the new cross-DM search feature, which now allows Discord users to search across all of their direct messages, which was also a really often requested feature. So overall, now we can look at our Search v2 system and see how we did. We now index and serve trillions of messages and have more than doubled our indexing throughput from Search v1. We run 40 Elasticsearch clusters, which have thousands of indices to house this data. And we've seen really big performance improvements. Our median latency for search requests is now under 100 milliseconds, with P95 and P99 less than 500 milliseconds. Importantly, also, we can now perform rolling restarts and upgrades with no performance disruptions, which also allows us to make improvements much more easily moving forward. So that's all for now. I hope that you've enjoyed hearing about some of our lessons learned from scaling search infrastructure at Discord, and thank you all so much.